Chapter 15 on equilibrium. And what equilibrium is a reaction that really doesn't stop. We've only been talking about reactions that stop, but equilibrium is when it kind of gets to its happy point, and it's where the forward reaction and the reverse reaction are actually occurring at the same rate. It's real important that you know this definition because this will be on your quiz, and I told them that, even though some of them are still missing it. Equilibrium means that the forward reaction and the reverse reaction are taking place at the same rate. Now, you don't have the same amounts, it's the same rate. And it does relate to kinetics, which is chapter 14. A rate, again, is how fast the reaction's going. So we actually have a double arrow going on. This Word document that I'm writing on is uploaded on Edmodo, and so you can print this off and follow along if you would like. So anyway, there should be a double arrow here. The arrow can be written like that, or you can write the arrow like this, but please do not write the arrow like that. Unfortunately, a lot of my documents have the arrow written like this, but this is not really truly correct. So when you handwrite it, if you'll write it like that for me or write it like that, that is known as equilibrium, meaning the reaction is going forward and backwards at the same rate. That does not mean, again, that we have equal amounts. And there is something called the K expression. And the equilibrium constant expression has a K, kind of like when we had this guy, we had the rate equals, and we had this little k, and we maybe put A. We had a reaction that's going on like A going to B. Well, now this reaction is actually going both ways, so we have a comparison between the rate of this, which would be something like this going on, and since these rates are equaling one another, these two make a constant, and that is really what's going on. So this is going to be actually a capital K, and so we write it as a capital K, and you'll see all kinds of different capital Ks. They're going to have little letters with them. The little letters are just going to mean different things as we travel through different chapters. So you don't necessarily have to worry about all the different little letters that are beside the K. Right now, if we go further on into on this little sheet, you'll see all the different K's that we're going to be dealing with: KC, KP, KSP, KA, KB, KW. These are all ones that we're going to be seeing in the next 3 chapters. So you don't need to memorize this. I just went ahead and put it in the Word document for you'll know that, hey, all these K's are kind of the same thing. So that was on the second page of the Word document. So when you go to write the expression, what you're looking at here is the little a is meaning the coefficient, and the big A is talking about the substance there. So we got A plus B, and has a coefficient of A and a little b in front of it, and you got making C and D, and these are representing our coefficients. So when you write the expression, if you'll notice, we've got brackets going on, and the brackets are raised to their coefficient power. We actually did some of these in pre-AP, but it's been a long time. K's are always written. The product side, which is always the right side, even though the arrow is going back and forth, the right side is still called the product side. They are going to be put in brackets, and that's going to be raised to the coefficient power. And this is going to be over the reactant side, raised to the coefficient power. And this is the way an expression, the little c is just standing for concentration. The brackets mean concentration, so this is how we would write it if we're dealing with molarities. And so it would be Kc. If we were dealing with pressures, pressures looks just a little bit different. Instead of, we would have the letter P, and notice instead of brackets we have parentheses. Instead of I was putting the reactants in. We're going to do a practice one here in a minute, so this will make a little bit more sense. You put parentheses, you put the big P, and your products will go down here as kind of like subscripts, and they'll be raised to your coefficient power, and they'll be over your pressures of your reactants, and this will be raised to coefficient power. Now you would use these for gases, and so these are always going to be measured in atmospheres. Maybe KPAs, but for the most part they're measured in atmospheres. So molarities are the brackets, the little p's are going to be atmospheres. And so I'm going to scroll down here. Every time I scroll, that disappears because I'm in Word document. So you can read here, it says the brackets with A and D are the molarity concentrations, and the P with the little a and D are the partial pressures at equilibrium, which is when it's going back and forth at equal rate. The products are in the numerator and the reactants are in the denominator. Coefficients in the balance become the exponents in the equilibrium expression. You may want to highlight, star, do something. This one right here is very, very important. We never put solids or pure liquids in our expression. They're completely left out of the expression. So you ignore them. So you're not. Well, I'll show you some examples in a moment. And then most of you will like the fact that number 5 is for the K, for the constant, you do not have to put any units. He's going to have so many different units that we just kind of just don't worry about his unit. So those of you who hate me putting -1 for the unit, you will not lose those points for the K because we're not going to worry about him having the unit. What the K is going to tell us is when the reaction gets to its equilibrium point, the point where the forward rate and the reverse rate are equal, it's going to tell us which one's favored. And I would highly recommend you know this for your quiz as well. If you have a really larger than 1K, that means that the products are going to be favored. One of the problems from the homework are going to give you a K and ask whether a product or the reactants are favored. If it's a really large K, the product's going to be favored. If it's a really small K, that means that the reactants are going to be favored. Favored means that when they get to their point where they're going to be at equilibrium and making equal amounts, not equal amounts, I'm sorry, when it's going at equal rates, there's actually going to be more product or more reactant in the solution there. Alright, so we're going to move on, and we're going to go down to the sample worksheet, and then I'll be coming back up. So I had this printed off. We'll be coming back to this in just a moment, and then we'll be coming back to Roman numeral 4. But we're going to look at the sample problem. The very first problem says the Haber process, which is a real important industry, which is the making of ammonia. It's the second most important thing that's made in the United States, which is the making of ammonia. The first one is petroleum. We had to Google that in class the other day, but ammonia is the second most. Ammonia is NH3, so if we're synthesizing it, it would be over here on the product side, and we're going to be making it from its reactants, which are going to be nitrogen and hydrogen. And I'm going to draw double arrows because it's going to reach a state of equilibrium. If we were to put it in a container for the nitrogen and hydrogen could not escape, or the ammonia could not escape, this thing would actually reach equilibrium. Ammonia is actually a gas. This is kind of important to write. Hydrogen is a gas, and then nitrogen is also a gas. Now this is not a balanced equation, so to balance this equation, I would need a 2 here, and then I would also need a 3 here. So there's my nice balanced equation for that. Our next one says write the equilibrium expression for the Kc and the Kp for this reaction. Well, the Kc is written with brackets. It's always the products on top, so we're going to put brackets. We're going to put NH3. We're going to be raising that to the second power because we're raising it to its coefficient power. And that is going to be over our products as long as they're gases or aqueous. We're going to put them in here as long as they're not solid or liquid with an L. So this would be N2, and this is going to be raised to the first power because the first power is the coefficient. We usually don't write ones, brackets, and then we're going to have H2, and that's going to be raised to the third power. And that's called the expression, the equilibrium constant expression. That is Kc. Kp looks almost identical. Instead of brackets, we're going to use parentheses. You would have a parentheses, and you would write NH3, and this would be raised to the second power, and then this would be parentheses, this would be a P, and this would be N2, and then this is raised to the first power, and then this would be H2, and this would be raised to the third power. And so that's called the Kp expression. So the Kc expression has brackets, the Kp expression has parentheses and big P's in them, basically, for pressure. And that's the way that would look. I did a few, for instance, with them. If I had an equation like this, where we had AgCl, that is a solid, if it were breaking down into Ag plus 1, anytime it's a plus positive or something, that's always aqueous because they don't form those ions unless they're in solution. Breaking down into water here, making those ions there. So if I wrote the expression for this one, if I did the KC expression for this one, its products, which in this case would be AG plus 1, brackets, times Cl minus 1. If it's an ion, I got to write it as an ion. And these are both going to be raised to the first power. And then it would be divided by the reactants, but the reactant is a solid here, so I do not even include it. So that's going to look just like that, leaving everything else. So that is my answer for that one. There's no bottom because technically you would have it over 1, so we don't need to put it. If we had something that looked like this, I did a little generic. If we had 2A, which was maybe a gas, plus 3B, which is, we'll just say he's a gas as well. And then we have this double arrow thing going on, and maybe it made 5D, and this 5D somehow became a solid there. So when we went to write our KC expression for this, you would not have a top because this is not get ridden. And I'll just tell you, this is what students tend to miss. They will put solids or they'll put liquids. In fact, let me go ahead and just change this for just a second. I'm actually going to make B a liquid for you can see. Okay, he's a liquid. So you don't put anything on top, so instead you put a 1. And then we're not going to put him either because he's a liquid, so we would put just A, and this would be raised to the second power. If I had left this B as a gas, then it would be B raised to the third power. So those are really, really easy. One of the homework problems is just going to have you do that. Actually, it's a homework worksheet. And Zach, if this is you listening to this, Tiffany, I gave Tiffany a copy of the worksheet for you. So unfortunately, I don't have a copy of that for you to do that I could upload to Edmodo. All right, let me go back to this. Let's go back here. Oh, one more. All right, we were back to this, and this is our expression. And so now it says if the concentrations at equilibrium is 0.01 molar ammonia, 0.02 molar nitrogen, and 0.02 molar. And here, this is real important, at equilibrium. That means I can take these numbers and plug them in. So I've got to decide if I'm going to put it in this one or this one. Their molarity, so I'm going to put it in this equation right here. So I'm just going to find, it says that ammonia is 0.01. So you got 0.01, and I would like you to put the M. It's going to be squared, and you're going to be putting that. And this guy is, nitrogen is 0.02 molar, and he's going to be to the first. And he's 0.02 molar, and he is going to be raised to the third power. You just put that in your calculator and solve. You should be coming out with 625. Has no units, so we don't have to worry about units. So that's going to be our KC because it's in molarity. The next question says, which is favored, your products or your reactants? And how can you tell? Well, this number is larger than 1, so our products are going to be favored, and how can you tell the K is larger than 1? Or you can say the K is larger than 1. So if the K is large, the products are favored. If the K is very small, the reactants are favored. So that's really easy, and one of the homeworks is going to have you do that. I'm going to scoot up here. Oh, unfortunately, I'm going to have to go to back and do it this way. Microsoft Word is not the greatest to work with here. Okay, our next question says, what is the KP for this reaction? I'll scoot all of these up here so I can see them. So, this is the KP for the reaction. Now, our reaction was, we had N2 plus 3H2 made 2NH3. Okay, that's our reaction. And we found that the KC was 625 from the one right above it. Well, we have an equation that allows us, and this was on the second page of the notes that I said we'll get back to. The equation which I will give you is that the KP is related to the KC by taking it by something called R times the T, which is temperature, raised to the delta N power. The KC we just found, which was 625. Okay, the R is a constant, and I will give that to you. It's also on the board. R is 0.0821. He's got some very ugly numbers, units there. He's got 4 units. I told him they didn't have to put the units, but I'm putting them for you could see that this is our temperature unit. Our temperature has to be in Kelvin. Unfortunately, I had to give him the temperature. I forgot to leave. I left the temperature out of this problem. The temperature of this thing is going to be at 25 degrees Celsius. There's 2 of these in the book, and they give you the temperature. Well, our temperature here, our T, has to be in Kelvin. And the way we go from Celsius to Kelvin, we got to add 273 to that. So from Celsius to Kelvin, you always add 273. That's going to make 298 Kelvin. So I'm going to put 298 right here. And I'm going to put the Kelvin. Alright, our last thing is this little delta N. Delta N stands for number or moles of gases. It's only about gases. It's not about anything else. This thing right here was a gas. This guy right here was a gas. And this guy here was a gas. The little triangle means change in. And change is always the final minus the initial. So in this case, it's going to be the products, which is the final, minus the initial. So if we look here, we've got 2 moles of gases here, so we've got 2 moles of gases on the product side, minus the moles of gases you have on the reactant side, which you have 3 and you have 1 there. You have a total of 4 there, so 2 minus 4 is a negative 2. So we're going to be raising this thing to the negative 2 power. And so if you do the math here, I do believe it comes out to be 1.04. This is our answer for I'm invading my space here, but this is our answer for number 5. Again, this is called Kp, which is for pressure. Really close to 1. What that means is the pressure at equilibrium for these gases is going to be really close to each other. So not really much favored as far as pressure is concerned. There's going to be about as much pressure of ammonia as there is of the other 2. And that's called the Kp. I did a couple more with them just to show. I just made up some things. I said if you had 4... A, which was a gas, and plus 2B, which was, we'll just make him aqueous. And then you did something like this of 3C, which is a gas. If you were doing the delta N for this, because that seems to be the hardest, you only look at the gases, so this is 3. And you don't look at him. Now he would go in the expression for Kc, but he doesn't look for this problem for Kp. It'd be 3, and it would be 3 minus 4, which would be a negative 1. Okay, so you only look at your moles of gases, and it is going to be your products minus reactants there. Alright, so we're going to go back to that is my answer for that one. So we're done with that. So this was 1.04. You're going to get the shortened version of this one. The next question said, now again, our equation up above, which I can't move because it'll, was N2 plus 3H2 makes 2 NH3s. And the K for this was 625. Okay. And the question's asking what would happen if we reverse this equation. Well, if we reverse this equation, you would end up with 2NH3, and that would then make N2 plus 3H2. So if we then did our products over our reactants, this would be on top, and this would be on bottom. So it would actually flip. Everything would flip. So when you're looking for the reverse reaction, to find the new K, you simply take 1 divided by the original equation. So 1 divided by 625. And I don't know where my calculator went, but 1 divided by 625, I think it was like 39,000 something. I forgot what the answer was. Oh, that was not the right answer. It is 0.0016. So now this particular K for this reverse reaction is actually very, very small compared to, and it actually is favoring our products. No, I'm sorry, that is favoring our reactant there. Because our reactant, since we flipped the equation, again, your reactants are always on the left and your products are always on the right. Even though the arrows are going back and forth, we're still going to label them as products on the left, sorry, it's getting late. We're going to label as reactants on the left and products on the right. Okay, so in this case, since it's a smaller K value, it would be favoring our reactant side, which would be favoring the ammonia. When we did this one, it was greater than 1, and so it was favoring our product side, so it was also favoring ammonia. So when you flip an equation to find the new K, you just put 1 over it. And then our last one here is if we were looking at a value where you're looking for this equation, so you're going to look and see how is this equation here different than this equation here, and hopefully you can tell that everything has been doubled. So this has been doubled from the 3 and from the 2 to a 4. So if that's the case, everything would be changed. This would be down to the 4th power. I actually had them calculated, but I'm not going to do that here right now. This would be to the 4th power, this would be to the 2nd power, this would be the 6th power. If you change this and you double everything the way you find the new, you take 625 and you raise it to whatever power you change it. So we're going to raise this to the 2nd power, so 625 squared. That's where I was getting that 39,000 from a second ago. 390,000. If we did sig digs, this would actually be 39100 if we were doing sig digs from above. Okay, so you raise it to whatever power you're using. So if you had an equation where you had A plus B and it was making C, and I told you the K for this was 42, well, this would be favoring the products because it's greater than 1. If I were looking for the flip of this one, this equation here, this is a synthesis reaction. Now I'm looking at a decomposition reaction. In order to find the new K, you would take 1 over 42. And I don't want you to leave it like that. I'd actually have you calculate it out, and you would actually put in 1 over 42 in your calculator, and you would get 0.0238. Okay, so that's that one. Then I told them, well, what if you had something like, what if you had, this one's 4, this one's 2, maybe that one's 4, and I gave you this equation. Let's see, we'll do 707, I don't know, I'm just making up numbers. So if you had 2A plus B there, I asked what would the new K be, and you have to look and see what I did with these two equations here. Well, I flipped it, so that's one thing I did. I flipped it, so I would take 1 over 707. That's going to account for the flipping. That's not all I did. I actually also halved it. So if you half it, you're actually going to raise this to the 1/2 power. Another way to say raise it to the 1/2 power is taking the square root. So you could do either one of these. And it doesn't matter if you square root it first and then take 1 over, or if you 1 over and then take the square root. You actually will get the same answer no matter which way you do it. Because when you raise things to the 1/2 power, it is the square root. And I'm getting 0.0376 for my answer there. So there's that one. So then I also did, what if you had 12A plus 6B makes 12C. How is this one related to this one? Well, I've increased it by 3, so you would take 707 and you would raise it to the 3rd power. You would do that. So 707 raised to the 3rd power. It was a really big number that I'm not going to write down. So you can kind of see. So you just change it to whatever coefficient that you would have. And that is actually explaining the rest part of the notes up here. It says when the stoichiometric, let me go back up here to this. We covered this this equation in the notes. We did that one, the moles of the product minus the moles of the gases. And there's your R constant that I'll give you. And here we go. Changing the coefficients. When the coefficients of a balanced equation are multiplied by some factor, the equilibrium constant of the new equation is the old equation, equilibrium constant raised to the power that you changed it by, which is I showed you examples. And this is the other one. When you reverse an equation, the constant for the reaction of a reverse is a reciprocal, or meaning 1 over the original. So that shows you if you flip it. The last thing is when you're adding two together. If you had, when we did the rate mechanisms, things happened in steps. And so if it happens in more than one step, in order to figure that out, say if this was step 1 and this was step 2, if you add these two together, can you see your intermediates there, and these two equations are making this one here. In order to find, this would be the K1 and the K2. In order to find the new K, you simply multiply these two together. So it's as simple as that. That times that equals that. So if you had something that was in step 1 and it was, the K was 2, and in step 2 the K was 3, and if the step 1 and step 2 with no changes added up and equaled the total, to find the K for the total, you simply multiply and you would get, not 5, you would get 6. K would be 6. Okay, so it's as simple as that. I don't think there's any of that in the homework.